Welcome back. I'm going to show you in this video how to make ethers using the Oxymercuration Demercuration synthetic route. You may recall from the addition lecture that when you treat an alkene with mercuric acetate in the presence of water, you end up forming an alcohol that doesn't undergo rearrangements in the process of making the alcohol, and you also produce it via the anti-configuration. And the reason that happens is because when you look at the carbon-carbon bond lengths, that of the single carbon-carbon bond being 1.54 angstroms, that of a carbon-carbon double bond being 1.34 angstroms, and compare it to the size of Mercury, Mercury is roughly the size of that entire bond length. So, and this, by the way, is just the radius, right? It's the ionic radius. It's not the full size of the Mercury. So the diameter of the Mercury, atom, if you were to treat it as a circle, is actually 2.32 angstroms, which is considerable, right? So that has more than enough room to be sitting on both of those carbon atoms, right? So if you have the alkene attacking your Mercury, you will produce this, so-called intermediate. But the truth is that the Mercury being so big and large, it's actually basically occupying both of these sites because it can sit on both of them due to its gigantic size, right? So in essence, you're dealing with this mercurinium ion, which looks a lot like a bromonium ion, right? And in essence, it's the same idea. The size of bromine is large enough that it can sit on both of those carbons at the same time, creating more stability for the carbocation being formed, but also restricting it to no rearrangements happening whatsoever. All right, now let's say that instead of water, you use alcohol as your solvent. All right, well, the synthesis scheme is still the same. You will add mercury to your alkene. The mercury is going to sit on both ends of those carbons, and the incoming nucleophile, which in this case now will be an alcohol as opposed to water, is going to attack the site that is the most bulky or the most substituted, because the mercury being big anyway, is going to try to stay away from the biggest site out of those two carbons. So this carbon here on the left side is the most substituted, and that's where the alcohol will attack. The mercury will basically get out of the way and produce the following etherate with an anti-configuration. Okay, now in terms of removing the mercury, because usually you don't want to have the mercury bound to carbon. Turns out that those type of compounds tend to be very toxic. Sometimes they're tolerable and can be used to treat other microbes that may be damaging or perhaps causing disease. But generally speaking, mercury carbon compounds are rather toxic, and many of them can be very toxic to us humans. So what we want to do is get rid of the mercury. And if you look at the electron potential diagram shown here, notice that mercuric ion is all the way up here, meaning that is the most oxidized version of mercury, but the hydride ion is all the way down here. And what this is telling you is that because these two regions do not overlap, if you bring them in contact with each other, in other words, if you mix these two reagents together, they will react. And what will happen is that the hydride will give its electrons away and be oxidized to dihydrogen, whereas mercuric ion will be reduced down to mercury, neutral mercury, elemental mercury. And the reason why is because now we have these overlapping areas. This means that these two species can coexist with each other. And mercury being a rather dense liquid, we're talking about 13 grams per ml. That's a really high density, 13 times higher than the density of water, perhaps even more. Once you produce it, this is going to be sitting at the bottom of your flask, your vial, and your organic solvent is going to be pretty much sitting on top of it. So all you have to do is just withdraw your organic solvent with a pipette, and that way you can separate it very easily from it. So this is actually a very convenient type of synthesis. Although nowadays we don't typically use it that much because mercury is actually toxic, and and environmentally speaking, people are just trying to get away from mercury, and we don't use it that often in labs anymore. Um, all right, so yeah, you can remove it by decantation, or you can just use a pipette and just pipette out your organic material. So the reagent that we use to deliver the hydride is sodium borohydride, and only one out of those four hydrogens is actually hydridic. The other three are covalently bound to boron. So when you do this, you do have to use one equivalent of sodium borohydride to make it happen. So what's going to happen is that your mercury is going to be reduced to elemental mercury. The sodium will take off with the other acetate component, so you'll kick out sodium acetate, and you'll also produce borane as a byproduct. But the more important result is that you will turn that carbon mercury bond into a carbon hydrogen bond, and the anti-configuration will still be retained, right? So one way to think of this, albeit not the correct way to think of it, is that when you bring sodium borohydride, the hydride is provided to the mercury, and the acetate comes off as a leaving group, right? So that's where your sodium acetate comes from. You also produce your borane in that step, and you could think of this as being your carbon mercury hydride bond, and this automatically will provide the electrons to the carbon while the mercury gets reduced. It takes the electrons out of this thing and ends up being produced as mercury liquid. But this is an oversimplification, not meant to represent the actual mechanistic step. What actually happens is that the reaction includes radicals. So it's a lot more complex than I'm making it sound right now. But the end result is still the same, right? You produce your ether on one end, the hydrogen is attached to the other end, and this is how you end up producing your etherates in a pretty good manner. This is a Markovnikov addition, by the way, so maybe kind of useful. So let me show you an example of when you might want to use this particular technique to produce your ethers. Notice that in this molecule, which is an ether, right, we have a secondary carbon over here, and over there we have a tertiary carbon. All right, so that is kind of interesting because neither of those carbons would allow us to undergo a Williams synthesis type of reaction, because that requires that one of these carbons be primary or at least methyl, right? So that situation is not met. So we cannot generate this alcohol via this route. And also we cannot necessarily do it via the acidic conditions, because other things may happen. So this kind of leaves us with the idea of, well, perhaps the oxymercuration demercuration may be the way to generate this particular ether. And what you can see right here is that, okay, well, you have here a tertiary carbon, right? Now that perhaps may be uh, the alkene that you want to produce or start with. And then what that will mean is that the section right here, your isopropoxy section, may be the alcohol that you want to start with. Okay, so let's make that happen. So this is cyclohexane with a methyl group. Notice that you want to end up with the ether on this position. If we were to make an actual alkene, the alkene will have to be right on this position, because remember, the alcohol is going to attack the most substituted site out of the entire molecule, right? So this will be one way of representing it. This is the kind of 3D way of representing cyclohexane with the methyl sticking out of it. Now the mercury, if it attacks the cyclohexane, or vice versa, if the alkene attacks the mercury, we're going to form that mercurinium ion that we talked about before, right? And here you will bring your alcohol, which will attack the more substituted site, which is the carbon over here. That will kick out the mercury on the other end. You have them producing the anti-conformation, right? And then at this point, you treat that reagent with sodium borohydride to ultimately kick out mercury, kick out borane, kick out sodium acetate, and of course introduce the hydrogen at this anti-position, which you don't need to actually draw it out, but that will be the way in which you kick out your mercury. And this will produce the desired product that you're trying to make. Okay, so that's it for oxymercuration demercuration. In the next video, I'm going to talk to you about how you produce the alcohols via condensations.